Hello students, let us calculate a second example. But before starting the second example, let us um, uh, understand or correct one value which we have considered repeatedly in our previous example. That in each case we have considered that the value of the value of excitation volt generated EMF, no load EMF, which is 233,558, but which is only 23558. Clear? In each case, just erase one extra 3. The rest of the value or calculation will not affected if we change this value. But by mistake, it is considered as 23355, but it is only 23558. Clear? So just consider this case and let's calculate a second example where it is given that a generator is delivering a 40 megawatt. Almost the same generator is considered which we have considered in our previous example. So the generator is delivering 40 megawatt with 30 kV generator terminal voltage. So the excitation voltage is 23558, which we have derived in previous example case A with an angle of 17.1 degree, and a synchronous reactance is 9 ohm per phase. So for this condition we have to calculate the power angle delta, armature current Ia, and power factor cos theta with when the following three cases: when the field current is adjusted for the following excitation. That means by varying the field current, or I can say by varying the excitation, what will be the effect in power angle delta, armature current Ia, and power factor cos theta. In previous example or previous case, we have considered the case of fixed excitation. And here in second example, by varying the excitation of generator, we have to examine what will be the effect in power angle delta, power factor, and armature current. So let us start the example from the case 1 where it is given that the excitation voltage is decreased to 79.2 percentage. Clear? So we have to calculate the new excitation voltage with the decrease of 79.2 percentage of your original excitation. So just write down E is equal to 79 point percentage of the original one, which is 23558. Just consider the magnitude as 23558 into 79.2 percentage. So we will get 18657 volt. 18657 volt. Clear? So for this case, we have to calculate the armature current, power angle, and power factor. So we know the equation. I will just write directly the equation of the delta, which is sine inverse P into XS divided by 3 EV. Clear? Or if you wish, you can write P3 phase, which is equal to 3 EV by XS sine delta. So from this equation number 1, we derive the value of, or we make a subject of delta. Just substitute all the values which is given, that P which is 40 megawatt, XS which is equal to 9 ohm, E which is, yes, E is equal to 18,18657 volt, and value of V we need to convert it into the per phase. So which is V is equal to 30 divided by 3, which is 17 point, I think, yes, 17.32 kV. So just substitute the value of all these parameter in this equation. So you will get delta is equal to 21.8 degree. Clear? And with this delta, we have to calculate the armature current. Again, we know the equation of armature current from the voltage equation. So we'll write direct the equation, which is equal to IA is equal to E minus V divided by J into XS. Clear? So if you substitute all the values, in this first case I will write all the values, so you can get the idea. Here 18657 with, now the angle is 21.8 degree. Clear? Minus 7320 with the angle of 0 degree divided by J9. Clear? The same process which you have followed in the previous example. So the armature current for the case A, where the excitation is decreased to 79.2%, is 769.8 with angle 0 degree ampere. Clear? And yes, for this case you have to calculate the power factor, and which is given by cos phi or cos theta, which is 0 degree. So for this case you will get the power factor is unity for case 1. Clear? Next, second case where the excitation voltage is reduced to, yes, over here the excitation voltage is decreased to 59.27%. So for the same case, just repeat the process as we have repeated in case A, which is E is equal to 23558 into 59.27%. Clear? So you will get the value of excitation voltage or new excitation voltage with this decreased one, which is 13963. Clear? So again you have to calculate the angle delta from the same equation. So I will write now the values, which is sine inverse P 40 megawatt x 9 divided by 3 into, now E will be 13963 into the V, which is 1732. Clear? So you will get the angle, which is 29.748 degree. Done? And for this angle again you have to calculate the armature current. So I will not write this whole equation again. I will write just the final equation and its final answer, which is 962.3 with an angle of 36.87 degree. Clear? Yes, the unit is ampere. Clear? So from the current phase angle you will get the power factor, which is given by cos 36.87, which is equal to 0.8 leading. 0.8 leading. Clear? Now let us calculate the case C, or third one, case 3. So we know very well the minimum excitation correspond to, yes, is calculate the minimum excitation below which the generator will lose the synchronism. And we know very well from the theory that the generator will lose the synchronism after delta equal to 90 degree or beyond delta equal to 90 degree. So I can say, or we can say that delta is equal to 90 degrees steady state stability limit. So at this value we will get the minimum excitation. Clear? At this value we will get the minimum excitation. So let us calculate the minimum excitation value. So we know the equation at delta is equal to 90 degree, or I can say T three phase is equal to 3 into EV by XS sine delta. Just substitute delta equal to 90 degree, P equal to 40 megawatt, V is equal to 17.23 and XS is equal to 9 ohm, and calculate the E for the same. So I will write the equation for E. E is equal to Pxs divided by 3 V sine delta, 3V sine delta. So you will get or substitute all the values, which is 40, Xs is equal to 9 ohm, 3 V is equal to 17.32 and sine delta, which is sine 90, is equal to 1. Clear? So you will get the minimum value of excitation voltage, which is 6.928 kV. Clear? So just compare the excitation values. In first case we will get around 18.65 kV. Then in second case we will get around the value of excitation voltage is 13.9 kV, and the minimum one, which is 6.92 kV, at which we can say that we will lose the synchronism if we further reduce the excitation, or I can say if we further increase the power angle delta. Clear? And for the same case we have to calculate the armature current IA, which is equal to E minus V by J into XS. Clear? So just substitute the value of V, which is 6.928 with an angle of 90 degree. Clear? With an angle of 90 degree minus 17.320 with an angle of 0 divided by J9. Clear? So the final answer for this case of armature current, which is 2073 with an angle of 68.20 degree. Clear? So with this angle, the power factor for the case 3, which is cosine angle of 68.2 degree, will get 68.2 will get, which is 0.37, and it is positive, which is a leading. Clear? So for the same case, for the same example, you have to write down the conclusion with varying this excitation voltage or generated EMF. What will be the effect on the power angle, a power factor cos phi or cos delta, cos theta, armature current IA, and the power angle delta. You have to calculate the or write down the conclusion based on if you will reduce the generator excitation, then you have to write the what will happen in power factor, armature current, and power angle delta. Clear? I hope you are clear up to this example. So in next session we will derive the condition of steady state stability. I hope you are clear up to this.